Welcome to this video on Kirchhoff's loop rule, also known as Kirchhoff's first rule. This is really a statement of energy conservation. And we actually looked at that in the last video when we looked at how we would track the energy coming into and out of the system of the circuit. The whole idea is that if I take the amount of work done by the battery and I subtract out the work done against a charge going through each of the resistors, that I should add up all of these values to 0. In other words, this minus this drop minus this drop minus this drop should all sum to 0. And we're going to take a look at how that can be very useful in solving different kinds of problems. We're also going to rename the battery now, the source of energy in a circuit, as the EMF. Now, EMF is actually an outdated term that stands for electromotive force and was used and come up with back in the time when the scientists didn't really understand that the battery wasn't really providing force to the circuit, but was really providing a kind of work done or energy done. But the acronym is still used to this day and is symbolized with just this fancy so-called letter E, which I poorly draw as a kind of backwards 3. Another thing that we're going to do is we're going to show conventionally here that with a little open circle and an arrow will point from the negative terminal of the battery to the positive terminal of the battery. This is showing that the potential increases from the short to the long terminal. In other words, if a little electron was pumped from the short to the long terminal, or a little positive charge truly from the short to the long terminal, the potential would increase. Now, you can think of EMF as being equal to the potential across the battery. Those are really the same thing for all intents and purposes, and we'll talk about some deviations from that as we go. We also want to keep in mind that because this is a conventional rule, we are always going to use conventional current direction. This is extremely important in some of the sign conventions, the SIGN conventions that are used when employing this rule. The idea here is that the EMF is an amount of energy, right, in terms of voltage. So we factored out, and if you've watched the last video, we factored out the value of charge throughout all of these work done, that will leave us with a potential rather than a potential energy. But the idea is still true. If you track the little electron through the circuit, if it starts here at the 0 terminal, it gains energy, moves through the wires, drops a certain amount of energy, drops again, and finally drops here, coming back to 0, and then working its way back around again. So what we would say is that there is a potential drop across each of the resistors when I travel in the direction of conventional current. Now, if you recall, conventional current will always start at the positive terminal of the battery and will work its way around back towards the negative terminal of the battery. So if I'm tracking in the direction of conventional current, Kirchhoff's loop rule is going to show the potential drops all added to one another. So in other words, I could write it as the EMF minus the potential drop across 1 minus the potential drop across 2 minus the potential drop across 3. These should always sum or add to 0. Now, the reason I keep saying add or sum is because what I'm saying here is that when I move in the direction of the current, I'm really adding the value here, which delta V is equal to I times R, but it's a negative value when I travel in the direction of the circuit element, the current moving through it. So what I could write here is the EMF minus I times R1 plus negative I times R2 plus negative I times R3 all sum to 0. Now what I would do then in order to get back up to EMF is I would have to add the EMF if I go from the negative to the positive terminal of the battery, like so. Now let's say that I wanted to add up the values in reverse order, and you'll see why this will be important later on. Right now it does seem a little silly to go against the current if you know the conventional current's going this way, but it does actually become very useful. If I add them up going in this direction, what I need to do is, instead of dropping potential across R3, I actually need to add the potential across R3. So I would write plus I times R3 plus I times R4 plus I times, sorry, this is R2, R1. And when I get to this point over here, as I go from the EMF, so I do going down this potential over here, I would do subtracted the EMF and I'd be back to 0 again. So we have to keep in mind that when you're moving in the direction of the conventional current, so in this direction over here, I'm going to have a potential drop, and when I move against the conventional current, I'm going to have a potential increase. So what the loop rule does is it essentially just writes out this full statement and shows that the energy is conserved all the way through. What this would allow us to do here is solve for a variety of different things. And we're going to see how that's going to pair with Kirchhoff's junction rule in the next video in order to help us analyze more complex circuits.